Jai Hind students, welcome to my YouTube channel. Students, what we learn with pleasure, we never forget it. What I mean to say is that if you do something you like, you will learn to get better at it with pleasure. So it's better to actually enjoy your studies than making it something to dread and worry about. With that positive note, students, let's begin this particular session. In this session, we are going to discuss an experiment so as to determine the spring constant of a given spring by plotting a graph between the load and the extension. So in order to perform this experiment, we need a setup. So let's first try to familiarize ourselves with the apparatus which we will be using during this particular experiment. Students, this is the setup which we will be using so as to determine the value of spring constant of this given spring. Now it consists of a stand which is having a firm base which is used to hold or clamp the given spring. And this is a hanger with slotted weights. It is to be attached at the free end of the suspended spring. As the slotted weights are increased in the hanger step by step, the extension of the spring is measured with the help of the vertical scale which is provided in the setup. So this is how, by extension method, the value of spring constant will be calculated. Let us consider a spring AB of negligible mass and length L0, and let it be suspended from a rigid support. When mass M is attached, then the spring, it will elongate to point C such that the extension BC is equal to L. Now students, on being loaded, the restoring force F will come into play and the spring will try to regain its original length. Now as per Hooke's law, the restoring force, which is denoted by capital letter F, which comes into existence when the body is loaded. Then as per Hooke's law, the restoring force is given by F is equal to minus KL. Now students, this negative sign indicates that while the extension in the spring takes place downwards, the restoring force acts upwards, that is in the opposite direction. And here K obviously is the constant of proportionality, which is known as the force constant, or it is also known as spring constant or the spring factor. It is actually the restoring force set up in the spring per unit extension in this spring. So that is how the spring constant is defined. And I have told you the significance of this negative sign, right? Restoring force acts towards the mean position while the extension is away from the mean position. Now students, in magnitude F, it may be written as KL. So K would be equal to F by L. So the SI unit of spring constant would be Newton per meter. So if you plot a graph between F and L, then as we are aware, F is directly proportional to L. That is, the graph between F and L must be a straight line passing through the origin, isn't it? So with the increase in the load, the extension of the spring will also increase accordingly. So this will be the nature of the graph which we will try to obtain during this experiment. And students, the slope of this graph will give us y2 minus y1 divided by x2 minus x1, which in this case would be L2 minus L1 divided by F2 minus F1. So the reciprocal of the slope of this graph, that actually will give us the value of spring constant. So first we will plot graph between F and L, and then finding the slope and getting its reciprocal, that will give us the value of the spring factor of the given spring. Now students, in order to plot the graph, we need to have different set of observations for different values of loads and corresponding the different values of extensions. So let's understand the procedure. When a load F suspended from low free end of a spring hanging from a rigid support increases its length by amount L, then F would be directly proportional to L. Or students, F equals to KL. Here K is the force constant or the spring constant of the spring. Now when this spring is unloaded, then the pointer shows a reading of 6 centimeter. Now we will hang a 50-gram hanger from the hook. The reading of the hanger is now 7.4 centimeter. Now students, we will gently add a suitable load of 50 gram. Now obviously the pointer tip, it will move down. Now the reading is 8.8 centimeter corresponding to 100 gram weight. Similarly, by adding gently another 50 gram weight, the pointer will further go down obviously, and corresponding to 150 gram weight, the reading of the pointer is 10.2 centimeter. So students, we are supposed to repeat this step, right? Now, if we again gently add a suitable load of 50 gram weight, then the new reading of the pointer is 11.5 centimeter. Now students, corresponding to 250 gram weight, the reading of the pointer comes out to be 12.9 centimeter. So that's the case of loading. Now what we do is, we will remove one slotted weight. Now the pointer tip moves up. So corresponding to 200 gram weight, the reading of the pointer now shows 11.5 centimeter. So students, we will repeat this step of unloading step by step. So by removing another slotted weight of 50 gram weight, we will be left with 150 gram weight, and the reading of the pointer now is 10.1 centimeter. Again, we will remove one slotted weight and the pointer tip moves further up. Now corresponding to 100 gram weight, the reading is 8.8 centimeter. And students, on removing another 50 gram weight, we get a reading of 7.4 centimeter corresponding to load of 50 gram weight, right? Now the hanger is removed. So we will get the reading of unloaded spring, which eventually comes out to be again 6 centimeter. So that's the case of unloading of the spring. Now students, this is the observation table. This is the column for the load on the hanger, that is the applied force. It is in gram weight. Students, 1 gram weight, it is equal to 980 dynes, right? And this is the reading of position of the pointer tip. Now this is during the loading in centimeters, and this is while unloading of this spring, right? And this is the mean value. Mean is x plus y divided by 2. So that's the mean value of loading and unloading. Now let us find out the extension in this spring when a load of 50 gram weight is attached, right? So what will be the extension? Initial reading was 6. Now the new reading is 7.4. So the extension would be L1 minus L0. So that would be equal to 1.4. Obviously it is in centimeter. Now students, when 100 gram weight is attached to this spring, then the extension would be L2 minus L0. This is the initial reading and this is the final reading, right? So in this case the extension would be L2 minus L0. So that is 8.8 minus 6. So that will give us 2.8. Similarly, when a total of 150 gram weight is attached in the hanger, then the extension would be, net extension would be L3 minus L0. L0 is the length of the unloaded spring, the reading of the pointer. So it would be 10.15 minus 6. So that will give us 4.15. Corresponding to 200 gram weight, the extension would be L4 minus L0. So that would be 11.5 minus 6. So that will give us 5.5 centimeters. And corresponding to 250 gram weight, the extension of the spring would be L5 minus L0. So that comes out to be 12.9 minus 6. So that is 6.9 centimeter. Now students, mathematically we can calculate the value of K corresponding to each observation using this formula of K equals to F by L. So K1, it would be equal to F, that is 50, divided by extension, that is 1.4. So that comes out to be 35.714. Obviously it will be in gram weight per centimeter. Similarly students, K2, it would be equal to 100 divided by 2.8, right? So that comes out to be 35.714. Again, gram weight per centimeter. Similarly students, the value of K3, K4 and K5 can be easily obtained using the same method. So K4, it would be equal to 200, that's the load applied, 200 gram weight, and the net extension is 5.5. So students, 200 divided by 5.5, you can check it, it will be 36.36. And corresponding to 250 gram weight, the extension was found to be 6.9 centimeter. So K corresponding to this observation would be 250 divided by 6.9. So that will give us 36.23. All these values are more or less the same, right? So actually, in order to minimize the error, what we do is we will consider the arithmetic mean of all these observed values. So that will give us the spring factor or the spring constant. So the spring constant of the given spring would be given by the arithmetic mean of all these observed values, which is K1 plus K2 plus K3 plus K4 plus K5. This is the sum of all the observations divided by total number of observations. So students, if you substitute this value and solve it, you will get 36.03. And the units would be, F is measured in gram weight and extension is measured in centimeter. So it will be gram weight per centimeter, right? This is the unit. Now we can also convert it in dyne per centimeter. So for that, what we do is, as students I have stated, 1 gram weight is equal to 980 dynes. So this will be in dyne per centimeter, right? So this will come out to be about 35,309.4 dyne per centimeter. Now students, let's convert it in SI also. Now you are aware 1 dyne per centimeter, it is equal to 1 dyne is 10 raised to the power minus 5 Newton, and 1 centimeter is 10 raised to the power minus 2 meter to the power minus 1. So it comes out to be 10 raised to the power minus 5 multiplied by 10 raised to the power minus 2 to the power minus 1. So it will be 10 raised to the power plus 2 Newton per meter. So students, remember this relation, 1 dyne per centimeter, it would be equal to 10 raised to the power minus 3 Newton per meter. So in case you want to express the spring constant or the force constant in SI, then we have to make use of this conversion. So 35,309.4 multiplied by 1 dyne per centimeter is 10 raised to the power minus 3 Newton per meter. So students, that comes out to be 35.3094. You can approximate it. So it will be 35.3 Newton per meter. So mathematically, the value of spring constant or the spring factor of the given spring in SI is found to be 35.3 Newton per meter. Now students, we intend to plot a graph between the load on the hanger and the extension produced in the spring for various values of F and L. So for that, x-axis is represented with the applied force, which obviously is in gram weight, and the y-axis, it is representing the extension in centimeters. And this is the scale I have used. Along x-axis, this 1 centimeter, it is equivalent to 25 gram weight. And here along y-axis, one box, that is 1 unit, it represents 0.75 centimeter, right? So let us try to plot the graph. First point is 0, 0. So obviously this is the origin. Second one is corresponding to 50 gram weight, the extension is found to be 1.4 centimeter. So corresponding to 50, it will be 1.4. So somewhere over here. So this is, let me write the coordinates as well. 50, 1.4. Then students, 100, 2.8. So corresponding to 100 gram weight, the value of extension is 2.8, somewhere over here. So 100, 2.8. Now 150, the extension is 4.15. So corresponding to 150 gram weight, the extension is 4.15. It will be somewhere in between 3.75 and 4.5. So somewhere over here. So this is 150 and 4.15. Then corresponding to 200, this is 200, the extension is 5.5. So it is 5.5, somewhere over here. So corresponding to 200, the extension is 5.5. And the last reading is corresponding to 250 gram weight. The extension is 6.9. 6.9. So again it will be between 6.75 and 7.5. Somewhere over here. So 250 and 6.9. Now ideally all these points must lie along a straight line. So let's find out. Okay, all these points are more or less lying on this same straight line. And students, as I mentioned earlier, the reciprocal of the slope of this graph, that will give us the value of spring constant, right? Now students, let us find out the slope of this particular graph, right? So let's consider this to be, suppose x1, y1, and let us consider this point to be x2, y2. So this is point A, this is point B. Now slope of the above graph, that we are aware, it is equal to y2 minus y1 divided by x2 minus x1. So that comes out to be 4.15 minus y1 is 1.4 divided by x2 minus x1, that is 150 minus 50. So slope of this obtained graph, it is equal to 4.15 minus 1.4, that will give us 2.75 divided by 150 minus 50, obviously it is 100. Now the value of k, as we have discussed earlier, it's the reciprocal of the slope, right? So it will be equal to 100 divided by 2.75, and on solving it comes out to be 36.36. And students, don't forget to mention the unit. So it will be in gram weight per centimeter. It will be in gram weight per centimeter. Now let us try to express this result in dyne per centimeter. So what we get is K, it would be equal to 36.36. Now students, as you are aware, 1 gram weight is equal to 980 dynes. So it will be in dyne per centimeter. Now as stated earlier, in order to convert this dyne into Newton, we need to multiply it by 10 raised to the power minus 5. So 1 dyne is 10 raised to the power minus 5 Newton. And on solving this, 36.36 multiplied by 980, you will get 35,632.8. Multiplied by 1 dyne is 10 raised to power minus 5 Newton, right? And 1 centimeter, students, you are aware it is 10 raised to power minus 2 meter. So on solving it, what we get is 35,632.8 multiplied by 10 raised to power, there is minus 5 and 10 raised to minus 2 to the power minus 1. That will give us 10 raised to power plus 2. So we will be left with 10 raised to power minus 3 Newton per meter. So we get 35.6328. So approximately 35.6 Newton per meter. So students, this is the value of the spring constant which we have obtained graphically, right? So this is in close agreement. This result is in close agreement with the value of the K obtained mathematically. So students, that's it from this particular session. I hope you must have enjoyed this session and thoroughly understand the concepts involved in this experiment, right? So students, keep watching my videos and don't forget to subscribe my channel and do share the link of my channel with your colleagues and friends, right? Keep watching my videos, students. Thank you.